Hello, everyone. Can you hear me? Okay. So, welcome to Nice AI Talk number 115. Today, we are glad to introduce Shandong Zhao from UC Berkeley. He is he is a postdoctoral researcher at Bayer Lab, and he received his PhD degree from UC Santa Barbara. And his research interest is basically to build increasingly powerful systems through scalable reinforcement learning and self-improvement. Today's topic is LLM reasoning with confidence.
Recording in progress.
And I'm today's host, Xiao Pan, and I'm currently working at Amazon as an applied scientist. So let's start. And Xuandong Zhao, you can start sharing your screen and start your talk.
Okay. Hi everyone. Nice to meet you all. This is Xuandong Zhao. I'm currently a postdoc at Berkeley, working with Professor Dong Song. Today it's my pleasure to introduce our recent works on LM reasoning. A specific focus is LM reasoning with confidence. We think confidence can be a very useful signal to help LM with the reasoning capability. This is a joint work with Zhuowei Kang, Aosong Feng, Sergey Levin, and Dong Song. To begin with, I want to highlight the recent progress of the achievement of LMs. In 2024 to 2025, the advancement of LMs mainly focus on the reasoning models. So we can see a lot of reasoning models come out, including DeepSeek R1, OpenAI O series, and a lot of like other models. So in 2025, we see that DeepMind, their reasoning models, and OpenAI's reasoning model even achieve superhuman performance in IMO or IOI. So reasoning models become very powerful in solving complex tasks or problems. So for someone who are not familiar with LM reasoning, I want to have a short intro. What is LM reasoning? From Elias' talk, he said predicting the next word lead to the real understanding, and predicting next token may in context may reduce the reasoning to the next token prediction. So from Danny Zhou's talk, he formalized reasoning as this format. We have the input and we want to get the output, and the reasoning is the intermediate steps or tokens that drive the correct answer. A core idea in current LLM reasoning is long chain of thought. So how do you understand chain of thought? Let's think about this simple question. Probably most of you have heard about that. ChatGPT is not very good at counting characters. I asked it how many A in Santa Barbara, and it answered with incorrect output with 4 instances of A, but the correct one should be 5. But when we ask the reasoning models, such as R1, it writes the chain of thought, like step by step by counting what's the character of each word and then how many A's are there. So the thinking process or chain of thought process have a very long context and can up to like 75 seconds. So we have say like the long chain of thought can have achieve very good reasoning capabilities, and currently people are very interested about approaches to scale reasoning. We have two type of scaling dimension. One dimension is parallel scaling. People use multi-agent systems to scale the reasoning, or it can sample multiple times for the same model. For the sequential reasoning, we can achieve the long chain of thought by prompting the LLMs or do the instruction following, instruction tuning (SFT) for the models. Another very hot topic is reinforcement learning for reasoning, which basically sets the clear reward for the models, and the large language model will automatically learn the chain of thought to achieve the correct answer. For today's talk, we want to focus on another dimension or another signal. Treat LLM's confidence as a first class signal for scaling reasoning, and we will address the reasoning with confidence in parallel and sequential settings, basically for best event selection in sample multiple times, and how to achieve reasoning, how to do reinforcement learning with confidence alone, and what's the relationship with reasoning capability. So today's outline, I have first covered the background of our reasoning, and I will introduce two papers. First is scalable best event selection for large language models via self-certainty, and secondly, I will introduce a paper, learning to reason without external reward. I will discuss several concurrent works and then motivate us for the open questions and conclusions. For the first work, a scalable best event selection for large language models, this is a work we did in the early 2025 February, and what we consider is best event selection. So as I said before, test line scaling or reasoning scaling can focus on like long chain of thought or sample multiple times. For the second approach, sample multiple times or parallel scaling, we have different choices. Let's think about if you have multiple answers, how to select the best of that. One approach is doing it with reward model, with process reward model or outcome reward model. And then given the reward score, you can pick the highest one. However, this is computation intensive. For each answer, you need to do an actual inference through the reward model. And moreover, such reward model is not generalized well. So a very good reward model in math probably cannot generalize to coding. And training such reward model require external efforts. Secondly, a very common approach is self-consistency or majority voting. Basically, you sample multiple times and then doing the majority voting on the final answer and choose a common answer as a final output. The limitation of majority voting is that it relies on the clear output. You need to have a very clear answer like A, B, C, D, or some specific number that can vote. It cannot handle open-ended tasks. For example, the code generation have different answers for each inference. Thirdly, probably we can also use LLM itself. The universal self-consistency basically is combine all answers from the large language model, put it in the prompt, and then directly ask which is the best answer. The limitation is clear. It's limited in sample numbers because of the context length or limitation of the input context window. Usually we see like it can only handle 8 number of samples for QM model or llama model. So our goal is to use LLM confidence to select good samples, and we will show such selection will overcome the limitation we said before. It is computationally efficient. It can handle open-ended tasks, and it have scalable effect on different number of samples. To begin with, I want to introduce how we calculate confidence And basically, we will calculate the sentence level confidence or distributional level confidence by leveraging the probability we get during the decoding. There are other confidence measurements such as verbalized confidence or like latent confidence, but what we focus on is the like confidence from the probability distribution. So for the token level confidence, we will calculate the probability for the chosen token. So for this example, we will only calculate the probability here. However, for the distributional confidence, we will consider the whole distribution. We will like consider all other candidates' words for this position. So the distributional confidence will have more information than the token level confidence. Yeah, here are some equations to calculate that. For sentence level probability confidence, we calculate average log probability or perplexity. So remember that these are only choosing the chosen token, focus on the like one token, and then do the average over all generated words. For distributional confidence, it is the average for all tokens, but for each token position, we will calculate a distributional level signal. One signal we can consider is KL divergence. The KL divergence is calculated with KL uniform distribution versus the next token probability distribution. So you can think about in this way, the lowest confidence one is you choose each token with the same probability. You don't know how to choose. That is uniform distribution. But if you are confident about this position, then the distribution will be very sharp or condensed. And it means that it is far from the uniform distribution, and we can use KL divergence to quantify that. Another metric is Gini score. It calculates the probability square, sum of probability square, and distributional perplexity in this way, and entropy in this way. So what we find, in short words, is like KL divergence distributional confidence is the best among all these confidence measurements, and we will show why. A very a connection to entropy of how we calculate KL is that entropy is basically calculating the the forward KL of probability versus uniform distribution. However, self-certainty is a calculating KL of uniform distribution versus the probability distribution. So the difference is that one is forward KL and the other is reverse KL. In other literature, such as RLHF, people have already used that technique to doing the probability distribution calculation. And these things that the forward KL is mode covering and reverse KL is mode seeking, so that the reverse KL can quantify the peak better than the forward KL. So other choice you can consider is F divergence, with basically calculating our other distributional distance. An example of how to calculate self-certainty can be visualized in this way. For negative entropy, it's basically P times log P over the uniform probability. And for self-certainty, is uniform times log P over log uniform versus P. So the probability here is like say 85, and the calculation of negative entropy and self-certainty is different. We will have we have such figure to show further evidence. The same entropy is not equal to same self-certainty. So for left figure, we show that one distribution is long tail distribution and another distribution is fat tail distribution. It has the same entropy around 5.0, but one distribution have very high self-certainty, but another distribution have lower self-certainty. For this figure, we show that the entropy and self-certainty with different distribution, and each distribution is a dot. So we see that they have like they have very high correlation, which means that higher entropy usually mean lower self-certainty. But if you consider a fixed entropy, it have a large scale of self-certainty. I hope this figure help you better understand how self-certainty that
Recording in
self-certainty
progress.
scales better, and it correlates with correctness. Moreover, it is not biased towards longer response. For this figure, we show that with more number of candidate response, range from 4, 8, 16, 32 to 64, and we will choose the best one of that based on the highest confidence. With different confidence scores, we show that the performance increase until we have 16 samples, but after that, a lot of other metrics have a decreasing effect. Only the KL divergence or self-certainty keep increasing the accuracy. So we think that based on this evidence, self-certainty scales better with more samples. On this figure, we show that incorrect
Recording
answer,
in progress.
and they have different shape, but like the bell shape with different mean value. However, for the negative perplexity, the correct and incorrect answer have a large overlap. So this figure shows that for even for the wrong answers, it may have high self-certainty or model is confident about, but from a global scale or the distributional scale, the incorrect answer have lower confidence than the correct answers. It's also related to the human's experience. If you are doing the homework or doing the exam, if I am confident about some questions, usually I will have better scores than the questions I'm very inconfident about. Okay, another effect is the bias. A strong
Recording in
bias towards
progress.
longer generations. And this kind of effect also reported in other technical papers. However, for self-certainty, we see that there's little bias towards the different level of response, and this effect help us with different kind of answers. Okay, another thing we want to emphasize is the voting. We said that we want to handle open generations, and then we can just choose the highest confidence one. But if we have clear answer, such as a math problem with clear answer, we can also use the voting method. Different from majority voting, we can do a weighted voting based on their confidence score and ranking. One particular thing is a
Recording in
hyperparameter
progress.
tune. And for this example, the three different answer and the self-certainty plus product voting, we'll choose the correct one because these two have very high confidence. Yeah, these are the experiment results for the general self-certainty and self-certainty with product voting. we can see with more samples from or the larger n, our results of self-certainty or broad voting keep increasing across different data sets. And then we also calculate with the reasoning models such as DeepSeek R1, Distill Llama. We see that self-certainty's performance outperform the first answer, the greedy answer, or the greedy answer, and our self-certainty with broad voting outperforms self-consistency. To sum up, we show that tasks without clear answer, for example, code generation, our approach self-certainty outperforms the best choice of uniform self-consistency, or USC. If we want to scale with the clear answer, like the math problems, self-certainty plus broad voting outperforms self-consistency. And a good property we have shown with self-certainty is that it correlates with correctness and it is not biased by length. So this paper is accepted in NeurIPS 2025, and after that, we are thinking about how to generalize that to other domains. Next, I will introduce our follow-up work using confidence as some reward signal for reinforcement learning. The title is Learning to Reason Without External Rewards. So this is a paper with collaborate with Song, Sergey, and Dang. Yeah, a background of that is from external supervision to internal feedback. The very popular RLHF and RLVR deal with the reinforcement learning for large language model from different aspects. For RLHF, we need human preference data to train a reward model and then use this reward model for reinforcement learning. For the verifiable reward, basically motivated by DeepSeek R1, people are care about the math answer and coding test cases so that they do not have the process reward, only care about the final outcome. And then doing the string matching, whether the math answer is correct, or doing the test cases on coding to use such verifiable reward for the reinforcement learning. And it do not require the reward model again. However, one question we have is, how about the task without verifiable rewards? There are a lot of tasks that is hard to verify. And we try to use model's confidence as an internal reward to incentivize its capability. So our assumption is higher confidence will lead to better performance, and we have witnessed such effect on the scaling, on the test time scaling of BES7, and this is also reflecting on some classical literature, such as the research did by Anthropic. They show that large language model mostly know what they know, so they mean that language model will show very low confidence for some difficult problems. But what they care about is only the final answer. And we will do it with a whole response. Another connection for the future I want to note is that for the future AI development, AI probably will reach superhuman capability. And then it will become increasingly difficult for humans to evaluate directly. We hope that learn from the internal representations or internal feedback will lead to better performance for the future AI development. And such effect also connect to weak to strong generalization using using weak supervision for the training of strong models. Yeah, a particular scenario we propose is reinforcement learning from internal feedback. During this scenario, what humans do is only to propose some difficult tasks. Then it gives to the LLMs or AI, and then the the AI will evaluate it internally, think about whether it is difficult or hard or easy. What's like the confidence about such problem, and then the model use internal feedback to update the policy to have better performance in the next round. So a particular instance we propose is called Intuitor with policy optimization, using policy optimization with self-certainty. Again, we use the self-certainty proposed in the Bessemer selection paper. It's basically calculate the KL divergence of uniform distribution versus a net token probability distribution. And then we do the average over all tokens in the response. And then how to do the training is in this way. Given the question sent to the policy model, the model will generate a group of answers, and then self-certainty score quantifies their confidence. We use such confidence as a reward to normalize and get the advantage, then train the model itself. For PPO and GRPO, they rely on the reward model or the verifiable reward, but our do not require that. We require the reference model to calculate KL divergence, and it can be dropped. Such KL term can be dropped. Okay, so to fit in the GRPO equation, the only thing we need to change is the reward part. So we only use self-certainty as a U here, and the advantage is calculated based on the self-certainty scores. And the intuitor is one example of RL from internal feedback, RLIF, with maximize the optimization goal as maximize the maximize the like internal feedback reward, and then also within the range of the KL term of policy model and the reference model. A quick summary of the performance of Intuitor shows that Intuitor matches GRPO on math tasks while achieving better out of domain generalization. So we train on the math data set with 7,500 problems, and then we evaluate on math datasets and code dataset. So for the math dataset, which is in domain, Intuitor achieved very good performance. It is slightly worse than we have external reward such as GRPO, but it's far better than the base model. A good thing is that it generalized better. If we just train on math and evaluate on coding, we see that Intuitor have better generalization than the GRPO. As we see very high score in live code bench and cruise eval scores. Okay, we see the training dynamics of the Intuitor and GRPO. For the Q1 2.5, 1.5 billion, a quite small model, the effect we saw is like it reduced the computation length from like 1,000 to 100. The reason is that for the small model, at the beginning, it will generate very long like repetitions, and then the reasoning will then the like our Intuitor or GRPO will forcing the model to shorter their response. And for the Q1 2.5, 3 billion, we see the similar effect as most people see during RL. The response length keep increasing with longer training steps. So GRPO-PV here is kind of using the majority voting results as a like proxy reward. which is also used in test time or reinforcement learning, TTRL, and other papers. Okay, during the training, we also see the emergence of long-form reasoning, and we see that Intuitor quickly demonstrate R1-like reasoning with the detailed steps and different blocks of planning and summarization and coding. We think the reason is that by using such like structured reasoning, the model will have better confidence about its own output, so that it will incentivize the output in this kind of format. So we do more analysis on the like reasoning format, and we see that for different ratio of answers, it will have more reasoning content than the initial steps. And for the coding scene, we see that from the initial training, it only have the code blocks, and then it evolves to have planning plus code blocks plus explanation. And after after a long training of Intuitor, the model will have step-by-step planning, code blocks, plus step-by-step explanation. And also with the increase of the self-confidence scores. Probably someone may think about reward hacking. We definitely see that during our experiments. One thing we want to show here is that whether we should use online model to give the confidence scores or offline model to give the confidence score. So from the figure, you can see if we use offline model, you can think about that model is a fixed like Cuban's 3BNN model base to give the confidence score and then use that as a reward to train an online version. With offline score, the model will increase the accuracy in the beginning, but will collapse afterwards. The reason is that it will easily find a very confident trace and then repeat such trace again and again. By using an online version of model to quantify the confidence score, mitigates such reward hacking scenarios because it's hard to find a reward hacking for a policy that keep updating. And but we didn't say that such online can totally solve the reward hacking. We also see some failure case after like hundreds of trainings, like towards like 500 steps, then the model may have some performance drop. But for the initial steps, like 100 to 200 steps, our performance keep increasing. Okay, another thing is distribution of self-certainty scores. So based on back to the best event selection, we show the incorrect and correct answers self-certainty score distribution. We do it again here. For the base model, we see that the correct and incorrect answer may have some little difference, but after training, we see that the Intuitor have larger gap of correct and incorrect answers, which means that the model is better at accessing the confidence of their correct and incorrect answers. We use statistical test to quantify whether they have significant difference of correct and incorrect answer scores, and we find that the Intuitor trained one have the lowest p-value, which means the difference of correct and incorrect answer under Intuitor is the largest. Okay, we see the performance on smaller models like 1.5 billion and 3 billion. We do it more with larger models such as 7 billion and 14 billion. The results shows similar ways. Our Intuitor outperformed a lot from base model, and it beats the GRPO trained model in terms of the auto distribution samples. Particularly, we want to show that for the instruction following evaluation, the alpaca eval integrator have very good performance compared to GRPO train 1 and Q1 train and the base model. So remember that we only train with mass training data set, and these are all out of distribution performance. We train some people also raise a question like whether this is due to data contamination, and there's paper showing that they even train QM model with random reward can lead to performance increasing. So we want to test about whether integrator is related to data contamination by testing on different model families. We trained on like Llama 3.53 billion and also the fully open model, OMO2. And we see the similar effect, like with more training steps, the accuracy keep increasing, and the completion length also increase. Yeah. Another thing we show here is comparison with entropy minimization and random reward. So entropy can be also think about some confidence measurement in the distribution level, and a lot of concurrent work use entropy as the proxy reward of confidence and then train the model. We compare the entropy minimization on the QN 1.5 billion, and the result shows that entropy minimization may not work well on this small model. The accuracy drops a lot, and then the repetition increasing, which means that it generates very long repetitions and garbage. On the right thing, we compare with the random reward, and the result shows that random reward cannot work on the 1.5 billion model, but our method, such as self-certainty or integrator, trained with self-certainty, can work on 1.5 billion. Yeah, these are some examples of evolution. Basically, it's like from initial step, it cannot do the question correctly, and after 30 steps, it will generate some reasoning steps, but still the answer is incorrect. And until the 40 steps, we will get a correct answer with detailed reasoning steps. Okay, a summary of this work. We introduce and explore reinforcement learning from internal feedback, RLIF, and one instance we propose is integrator, an RLIF-based model that utilize a model's own internal confidence measurement as a sole intrinsic reward. Integrator matches supervised RL performance on in-domain tasks while achieving superior out-of-distribution generalization on like coding or instruction following data sets. We uncover emergent structure reasoning and enhanced intuition following capabilities induced by intrinsic rewards. Next, I want to quickly show some concurrent works and to like show the landscape of current unsupervised RL. One similar thing is TTRL. The main difference is that they are using the majority voting result as a pseudo label, then train the model on such pseudo reward. We compare with TTRL, and we say that this is GRPO plurality voting, and our integrator outperforms that in the out of distribution samples, like the LICO bench and Crux Evil. Yeah, another thing is SRT, which is also using majority voting as a pseudo label to train that. Yeah, a similar paper, they use semantic entropy as some confidence measurement and combine that with ground truth, then do the like uncertainty aware advantage calculation. The unreasonable effectiveness of entropy minimization in algorithm reasoning, they explore using the entropy as a confidence, and then explore inference time scaling and RL. And their conclusion is that using entropy minimization as a goal with RL have the best performance. Yeah, maximizing confidence alone improves reasoning. This paper used entropy as a confidence alone as an internal reward feedback. Spurious reward, I have discussed this. They say that using random reward can increase the probability, increase the performance on QA models, but can not work on OMO too. But I have shown that using our intuitor can also improve the performance on OMO. So the entropy become very important in recent literatures, like entropy mechanisms, and also some people use entropy to choose like 80-20 ratio of different tokens. And self-evolving also related to such like RLIF scenarios. Yeah, some concern I have and all the community have is that whether such performance improvement due to the data contamination. Our short answer is probably not, and also because we show that it also works on OMO models. Secondly, does RL sharpen the distribution or create new skills? So this is a very hot debate, and I do not have very clear answer for that. And some people say you only test about like small QM models up to 14 billion. We do not know whether it works on like 100 billion parameter MOE models. Another thing I have mentioned is it may limit the exploration. For this kind of experiments, they show that after around 300 steps, reinforcement learning from internal feedback may have the dropped performance. So, but with RLVR, the performance will keep increasing. So this is a very interesting phenomenon, and a lot of concurrent works or recent papers try to solve this with different strategies. Yeah, and this is why does LLM sharpen the distribution or create new skills? And such paper discuss that. Finally, I will end up with some open questions and conclusion. For the open questions, the first one is why does RLIF work? What theoretical guarantees does it have on which type of tasks it is more effective? There are some existing works study that, and some short conclusion is once the model has the generation and verification gap, and then the self-improvement may help close the gap. But for some tasks that it's very hard to self-verify or do not have self-conscious, then it's hard to close the gap. Secondly, what's the best metric for self-confidence? We have discussed using a lot of different metrics like perplexity, entropy, or self-certainty. We show that self-certainty outperforms other metrics, but it may not be the best metric. People may start thinking about what are other choices and better choices. We only evaluate on some easy evaluated tasks, but our problem is we do not have very good open and reasoning evaluation benchmarks to do good evaluation. And I think community should think about how to create better open-ended reasoning benchmarks. Another open question, can we use self-confidence to select data or token? There are some existing work like using entropy to select token to do the gradient update. And we think using self-certainty or other confidence metric can also do this and may also have influence on how to select what are good data to train. Can RLIF scale to larger models? Is it more prone to hallucinations? What's the relationship with memorization? Yeah, these are some concerns about the model, and we want to see like whether RLIF can like reduce, can be some signal to reduce a hallucination. Can RLIF work together with RLHF and RLVR? How can their strengths be combined in different scenarios? My takeaway is that for some tasks that with clear reward, definitely you want to use RLVR because why not like just drop the because you already have the answer, then you can do this. But for some tasks that is do not have answer or you want to do test time scaling, then RLIF can be a good alternative or good approach to try. And we hope in the future, RLHF, RLVR, and RLIF can be combined together to fully push the frontier of model capability. Finally, is RLIF also applicable to agent-based tasks? And I think there's a lot interesting direction to explore. Okay, finally, I have some speculations to share. I think both entropy and self-certainty work. Self-certainty performs better on smaller models, and entropy is prone to repetitions because it have a bias for different length. And if the base model is strong, different RLIF variants can be effective. Instruction-tuned models are harder to further optimize via RLIF because behaviors is fixed and style is hard to adjust. Finally, some experience we have is Intuitor is sensitive to prompts because those prompts are the only human provided signals. So if you try with one setups that RLIF doesn't work, you should give a second chance by changing some system prompt or use prompt differently. Okay, thanks for listening, and I'm happy to answer any questions you have.
Thanks, Shandong, for the very inspiring talk. And we do have a lot of questions coming from the audience. So yeah, so I see the first question is that after the reinforcement learning, especially the training with the intrinsic signal, will the model demonstrate some overconfidence behavior? Like the correlation between the confidence and the accuracy is becoming weaker. So, and how to solve that kind of issue?
Yeah, that's a good question, and I already discussed it here. Like, if you train this with a very long time, like after 300 or 400 steps, then such internal feedback may be not accurate and lead to performance drop. And indeed, we have witnessed a similar effect with Intuitor. So the limitation of that is like after so many training steps, the cred and incred answer may have like overlaps more than like Intuitor initial steps. So some follow-up works, such as here I have show they already explore some combination of RLVR and RLIF together. Like they split the question to 4 different scenarios, like CRED 1 with high confidence, CRED 1 with low confidence, INCRED 1 with high confidence, and INCRED 1 with low confidence. And with different type of questions, they can have different signals to incentivize that. Yeah, I think this is still an open question, and yeah, but you feel free to read some recent papers on the follow-ups.
Thank you. And in your papers, you mainly focus on the reasoning task like math and the coding. But is have you ever studied about the hallucination? Will the self-certainty trained model show more hallucination than the original like RLVR trained models?
Yeah, so for the hallucination, we evaluate on the simple QA dataset, but I didn't show the performance here. The interesting thing is that the simple QA performance increase rather than decrease. So I think with like appropriate amount of intrinsic training, not too long, then the hallucination should be dropped rather than increased. And yeah, to fully understand the hallucination, the relationship of the confidence and hallucination, I encourage you to explore as an open question. And I already see some like yeah papers discuss about models' own intrinsic signal and the hallucination rate.
Yeah, thank you. And yeah, I see some questions mainly are mainly concerned about the assumption that the higher the self-certainty, the better the performance. So actually, it does that hold true in the what if like a response is incorrect but have a high confidence?
Yeah,
And how to do the calibration.
yeah. So that's a good question. I want to emphasize that for the incorrect answers, like the green region, the orange region, it may also have very high self-certainty scores. However, why we use that is because correct and incorrect answer, their like overall distribution have slightly is different, so that we can use the population level like difference to train the model. We do not say like for a particular sample, the confidence and their correctness is strongly matched. So promising literature or approach to try is how to calibrate that. And yeah, I think to calibrate that well can lead to better performance. So a difference I want to also note is that so there are a lot of like confidence calibration literature, but they only care about the final answers probability. Instead, what we care about is the whole response confidence. So we should take that into consideration.
Yeah, and yeah, we do have a lot of questions. So the next one is that how do you design the self-certainty, and will there be any upper bound for RLIF? I think this question is basically asking about limitation. So the original audience question is that will there be any upper bound for RLIF?
Yeah, yeah. So I have discussed it here as concerns. So there are some hot debate like whether our reinforcement learning can incentivize reasoning beyond the base model. And my speculation is cannot. But it depends on like how you translate that. So the basic thing is they compare pass at n versus pass at 1, and n can be very large. N can be like 10 to the power of 10, like billions of time. Then the base model can sample a correct answer, and then RL reduce that to like several trials. ROIF, I think the capability is bounded by the base model as well, but we see that it cannot um, beat the RLBR if the training step is so long. Then Because if you train with same data for many epochs, then it will become very familiar with these questions and very high confidence for the existing ones. A very interesting problem or open problem is to try with fresh data for like different domains and then to quantify the confidence. Yeah, my takeaway or my speculation is during the very open domains, sharpening the distribution like RLIF or Intuitor can help with the performance.
Yeah. And so I agree. Yeah, and I think by combining the RIF and RVR, we can definitely develop a better combined training schema. And I see that as you recommended me as the reading material, there is a new work this year, at the end of this year, about the semi-supervised reinforcement learning that combines both the RIF and the RVR. So
Yeah.
I think that combined method improves the training efficiency and further improves the upper bound of the RL training.
Yeah.
And yeah, another question coming out. So why self-certainty is better than entropy? So basically, why the reverse KRL divergence is better than the forward KRL divergence, right?
Okay. Theoretically, we do not have a very clear answer. It's basically like reverse KL versus forward KL. There's some literature to study the reverse KL versus forward and reverse KL of reference model and policy model. They do it like they have some analysis on that. But what we do here is some probability distribution of uniform and the current token probability distribution. So there's not much theoretical findings. What we do is we have some empirical findings like the KL divergence, the scaling of best of n is better than entropy, and then the entropy also have a bias towards like longer generations. We also do this is for the inference best event selection, and we also calculate it here with entropy minimization as a reward. It cannot work on small models. So these are mainly empirical findings showing that self-certainty is better than entropy.
Yeah, thank you for the summarization. So there is an audience asking about what's the advantage of internal confidence signals over the verbalized confidence scores.
Yeah. Okay. So I think to sum up, I have the following like summary. Like first of all, the verbalized confidence is not accurate. It relies on the model to have instruction tuning on such tasks, and yeah, so verbalized it cannot express very like fine-grained skill. It may have like high, low, or medium these like categories, but it cannot have like 1.5, 1.6, 1.7 those small difference. And another advantage of internal token level calculation is that it do not have actual um, compute burden. You can get that directly from the inference because you need the logics for every token, and then automatically you can get the self-confidence score of self-certainty or entropy. For the like verbalized confidence, you need actual token for each task, and whether that will destroy the whole task framework or flow is unknown. So yeah, I think these are key differences. And yeah, as I mentioned at the beginning, the confidence have different format. It can have formalized confidence, latent confidence, or this kind of token level, distributional level confidence.
Yeah, I think that is good summary. And let me see. I think all the audience questions have finished, but I do have some question of my own. So I think you have answered part of my questions, but I do have additional questions. Like the first one is, so there's very few e- computational overhead of applying this self certainty score in the inference time, but I think there should be some overhead during training time, because during training we don't need to take a look at all the scores after the softmax to calculate the score for the back propagation. But if we introduce self certainty as the reward, and we do have to like look at the full vocabulary. Is
Yeah,
that
yeah.
yeah?
So the answer is that if you look at the final expression, it have the for the whole vocabulary, and then for the whole response, you need to have the log probability or logits for every token. So this can cause some like memory burden or overhead. But the solution is you can do it with online average. So only keep the like previous average and then plus the current average. So it can there's some easy fix to reduce the memory, and I think with that there's almost no overhead at all.
Yeah, got it. And and another question is that as you emphasized throughout your presentation, that in Twitter training improves out of domain performance better than the RVR in especially in the experiment you have done in your papers. So do you have a insight into why does that happens?
I think our explanation is like it may because confidence is kind of work in different domains, as we show in the first paper. It work on like math and coding, and if the model learn to utilize their confidence to do such tasks, it can perform well on these domains. Yeah, but why it outperform better than GRPO? I think it, these are just some heuristic explanations. And so what we find is that so for this part we show that actually after intuitor training, the model can better separate the incorrect and better incorrect and correct answers. GRPO also improves such performance, but it's not as good as intuitor. So with this kind of capability, it may be like beneficial for the performance of auto domain tasks.
Yeah, that is yeah, a good perspective to explain that behavior. And yeah, I think I'm done with all my questions as well. And thank you, Shendong, for today's very interesting talk. And I see that this is a very hot topic this year. And we are looking forward to see more interesting talk in this direction. And yeah, I think if you have any takeaways for the audience, you can we can have 1 extra minute, and after that we can end our session.
Uh, yeah. So yeah, I'm excited about this direction because I think for solving open problems is the future direction for LMs. it can be done with reinforcement learning, also like self-evolving. We have seen the alpha evolve and other cool works. I think yeah, this will be a future direction with very high impact and encourage you to yeah also study this and have any interesting idea we can discuss together and explore together. That's all.
Yeah.
Thank you so much.
Recording
Thank
stopped.
you.